Let's record the third hour of today's lecture. I guess everyone is okay to hear my voice. If any problem, please leave a text message to me, TA. Okay, let's see, where's my electronic pad? Okay. Okay. Let's see. We have a total 81 students in my enrollment. My roster, I have confirmed the 81 students. So I hope by the end of this week, please study what today's lecture. So if you're joining this live streaming class, then I'm going to mark your attendance by myself in iCampus. So you don't need to play the recorded movie clip again. But the condition is your duration time for this lecture, connection duration time is uh, longer than 120 minutes. So otherwise, I cannot give you the attendance mark. Okay, so keep connected, stay tuned. Then you'll be okay. You don't need to play the recorded movie file again. Okay. So in this lecture note number 6, we're gonna study intrinsic Fermi level. Previously, we have learned the Fermi energy level, but this time we're gonna study intrinsic Fermi energy level, E sub I, denoted as E sub I. Okay, and the determination of E sub F, how to get this energy level, E sub F, the degeneratedly doped, or simply speaking, heavily doped semiconductor. So we'll study that. We'll study that later. And carrier properties. So this would be introduced in chapter 3.1. Okay. So I guess the thing that I did is right. Okay. So let's go to understand the intrinsic Fermi energy level, E sub I. So E sub I indicates, the Fermi energy level in an intrinsic semiconductor. Okay, so E sub F, to find the E sub F in an intrinsic semiconductor. In other words, to find E sub I, right, we can use the fact that the electron concentration is always identical to the hole concentration in an intrinsic semiconductor material. So from the thing that we have learned to describe electron concentration in an intrinsic semiconductor, that is NC times exponential minus EC minus EF over KT. And we can use another equation for hole concentration, NB, effective density of states for valence band, times exponential EF minus EB over KT. Okay, today we have learned it, right? And then let's rearrange all the terms to find the Fermi energy level. Okay, so here is a Fermi energy level, here is Fermi energy level. Let's do some simple math work. So NC over NV exponential minus EC minus EF over KT is equal to exponential minus EF minus EV over KT. And take a log for both sides, and you will get ln CNV plus ln exponential stuff is equal to ln exponential something, right? So following a few more steps and then rearrange all the terms with respect to the Fermi energy level, you will get this equation. So you can do that by yourself. Then these two terms, right, consists of and defines the intrinsic Fermi energy level, because this EF has been obtained from the fact that N is equal to P. This is only valid in an intrinsic semiconductor. In a doped semiconductor, N should not be equal to the P. Okay? So using this fact of N is equal to P, we can estimate the Fermi energy level that is matched to the intrinsic Fermi level, because E sub I indicates Fermi energy level for an intrinsic semiconductor. Okay, now plug in some effective density of state equation here and there, NB and NC, and you can do some more math work, and you're going to end up with another equation for intrinsic Fermi energy level here. EI is equal to the same, EC plus EV over 2 plus a little different, but instead of using effective density of state, here we used two different terms. That is, effective mass of here, N indicates electron, P indicates a hole. Okay, so effective mass of electron or effective mass of hole. So EP asterisk, MN asterisk. Okay, basically, effective mass of hole is a little bit lighter than the effective mass of electron in silicon crystalline material, so that here this whole term becomes less than 0, negative. So the precise location of intrinsic Fermi level is very close to the mid gap, but slightly lower than the mid gap, because this second term is negative value, because M sub P is smaller than the MN asterisk. So if I draw C, V, and here is intrinsic Fermi level, but this EI approximately in the middle, but in more precise, that E sub I is slightly lower than the exact middle point. So EI is placed near the midpoint, mid gap, but slightly lower than it. All right, that's all for intrinsic Fermi level. We're gonna use it a lot. E sub I indicates, simply speaking, mid gap. Okay, in band gap, EI indicates the middle point of the energy band gap. So with that in mind, let's move on to the next one, N and P. Now, as a function of Ni and E sub I. Previously, we derived this equation. In an intrinsic semiconductor, the electron concentration is equal to the intrinsic carrier concentration. For example, at room temperature, N sub I is 10 to the 10 per cubic centimeter. And we can rewrite it with the effective density of state and the conduction band minus E sub I. Okay. Previously, we used E sub F. Now we are talking about the intrinsic semiconductor material. So instead of EF, we can use E sub I. So I have write down EI. Okay. Then now, from this equation, let's derive effective density of state for conduction band. N sub C is equal to this. Okay. And now, the final destination is we would like to write down the equation for electron concentration as a function of Ni and EI. We don't want to use N sub C, effective density of state. Previously, the electron concentration has been written as a function of, or it has, the effective density of a state. we don't want to use it anymore. So for that purpose, let's rearrange the equation again. So N is equal to NC, right? So instead of NC, let's use this guy, Ni exponential C minus EI over KT. Okay, and here, okay, that is corresponding to NC. And NC times the equation that we have learned, I guess that was exponential minus EC minus EF over KT. Please remember the equation N is NC exponential minus EC minus EF over KT. This equation, I'm using this equation, but we can replace NC with this, okay? Then here E sub C minus E sub C are cancelled out. So Ni times exponential here minus plus. So EF here minus EI over KT. So now electron concentration has been rewritten with Ni and EI. Okay, here again N is rewritten with Ni and EI. And what was the position of the EI? That's almost in the middle of band gap. And what was Ni? At room temperature 300 Kelvin, N sub I is kind of constant, 10 to the 10 billion per cubic centimeter. And this is middle or mid gap, middle point of energy band gap, mid gap. Okay. So here, the very, I guess you should remember this equation to get a high score in midterm exam and final exam. Please remember it. The electron concentration N is very associated with Fermi energy level. These two. Okay. So if Fermi energy level, suppose that EC, and here is intrinsic Fermi energy level. Your Fermi energy level is here. Then once you know the EF minus EI, I'm talking about this term, power term, right? Once you know the EF minus EI, which means you know the electron concentration. Okay. So let's move on to the next example first. I will get back to the previous slide soon. If electron concentration is 10 to the 17 per cubic centimeter, then where is Fermi energy level in energy band diagram? This is really, really important. Definitely, I'm going to use this question for your midterm exam. Please keep concentrating. Keep your eyes on this question. Where is the EF if electron concentration is 10 to the 17 per cubic centimeter? Which means there are many free electrons available in conduction band, right? And if I add them up, if I count how many electrons are there per cubic centimeter, then it turned out that 10 to the 17 per cubic centimeter. Then question is, where is EF? Here, here, or here? Where? 1, 2, 3. Where? So going back to the question, N is equal to Ni exponential EF minus EI over KT. Previously, we used this equation, N sub C times minus EC minus EF over KT. But let's do not use this equation because of this effective tensile state. It's a tricky number. So we can use intrinsic carrier concentration. Again, intrinsic carrier concentration n sub I 10 to the 10 at room temperature. And we know this the position of the intrinsic Fermi energy level, mid gap, right? And we don't know the position of Fermi energy level. We don't know the electron concentration. However, in this question, the author has given the number for n, that is 10 to the 17. Then you can calculate the EF. Let's do this simple question. Simple calculate 10 to the 17 is equal to 10 to the 10 times exponential EF minus EI over KT. And let's move this term into the left-hand side. 10 to the 17 divided by 10 to the 10 is equal to exponential EF minus EI over KT. Then let's take logarithmic for both sides. Then let's write down the right-hand side first. Ln exponential something is equal to something, right? So EF minus EI over KT is equal to what? Here, left-hand side. Ln into the 10, 17, which is equal to ln 10 to the 17 minus 10. Okay. Now we would like to know the position of Fermi energy level. So EF is equal to what? So it's KT is moved to the right hand side. So KT and then 10, 17 minus 10. And the EI minus EI has been moved to the right hand side. So EI plus. Okay. So we are almost done. Take a look at here. The Fermi energy level is equal to what? Mid gap plus what? Okay, so mid gap is on the right and left hand side. You can see the dotted line indicates the E sub I mid gap. So EC, EV, the middle point. Okay, and plus what? Plus KT ln 10 to the 17 minus 10. So here 17 minus 10 can get out and move here. So EI plus 17 minus 10 times KT ln 10. So what is this number, KT ln 10? KT is 26 milli electron volt. And if I multiplying ln 10 to the KT, and this value times ln 10, using a calculator, we're gonna get this number, 60 milli electron volt. In other words, 0.06 electron volt. So KT ln 10 is equal to 0.06 electron volt. Plug in here, 0.06 electron volt. And here 17, where does it come from? The doping here, the electron concentration, 17. Maybe that comes from the donor's concentration. So donor concentration is 17. And intrinsic carrier concentration is, 10 billion. You remember this number, 10. 17, 10, 17, 10, 17 minus 10. So in doping concentration, just ignore the first digit, 1, and leave the second digit, 7. So that is equal to EI plus 7 times KT ln 10. So that is equal to 0.06 electron volt. So Fermi energy level is equal to EI plus 0.42 electron volt. Okay, so remember this number. Where does it come from? 60.06, 6, right? 6 times 7. Where does it come from? Doping concentration is 17, so take out the first digit. So 7 times 0.06. So remember this number, then you will get the position of the Fermi energy level is here, and the energy difference EF minus EI is equal to what? From this number, let me raise it. Here's 7. Take a 7. 7 times what? 0.06 volt, electron volt. So 0.42 electron volt. That's it. So you don't need to do this very complicated mathematical derivation. Don't do this anymore. Just ignore it. Just take this number 7 times what? 0.06 electron volt. And you will guess the precise location of Fermi energy level in the band diagram. Okay. So using this equation, well, the basic equation that we have used is n is equal to ni times exponential ef minus ei over kt. This is the essential equation that we have used, but it looks complicated. Just remember how to estimate the position of Fermi energy level for the doping concentration has been given and known. And take a first digit and times 0.06 electron volt. Then you will see the EF minus EI value. Very simple, right? So herein, let's practice one more question. Let's do this here. One more question is, suppose that that is 10 to the 15. Where is EF? Very simple, EC, EV. So for a given energy band diagram, in the middle, there is intrinsic Fermi energy level. Question is, where is the Fermi energy level? 10 to the 15, take a 5. 5 times, so EF minus EI is 5 times 0.06. So draw the Fermi energy level, and this energy difference is 0.3 electron volt. So since this band gap, half band gap, right? So total band gap is 1.12 electron volt. So half of it is 0.56 electron volt. Now, here to here is energy difference is 0.3 electron volt. Looks reasonable, okay? So you can do this simple math work. Once you can do good job in multiplying the number times 0.06 electron volt, that's it. Let's do another work. This would be a good simple E sub C, E sub V. Here is EI, and here is EF, and this energy difference is 0.54 electron volt. Is the electron concentration of the sample with this energy band diagram? It's very easy. 0.54. Okay, 0.54 electron volt. Okay, that indicates EF minus EI, and that is something times 0.06 electron volt. What is this value? 9, right? So this answer is 10 to the 1, bring the 9. So the doping concentration, say, and donor's concentration is 10 to the 19. Then since all the donors are fully ionized, so the total electron concentration is equal to the donor's concentration. So N is equal to 10 to the 19. And still, do you want to use this very complicated equation to get the precise position of Fermi energy level? Don't do this. You can use this simple work. Okay. In midterm exam and final exam, I don't want to use a very complicated number such as n is 5 times 10 to the 17. Where is the EF? This type of problem, I don't want to use it for your midterm exam. Okay, so very simple number. 10, say n is 10 to the 15 or 10 to the 16, 17, 18, 19. Those kind of simpler number will be provided in your midterm exam. Okay, so use this. Once you have successfully derived how this equation has been obtained, then you can use the relationship, the doping concentration and the precise location of Fermi energy level. So now, from the very first lecture note, did you remember the title? That was what is a semiconductor? And we have learned the two-dimensional bonding model, afterwards energy band diagram to express the amount of energy of a certain electron has. Afterwards, we have learned the doping, donors, acceptors in bonding model, as well as in energy band diagram, donors energy state and acceptors energy state near to the band edges. Afterwards, we derived a kind of complicated equation to have a relationship to associate the doping concentration or electron hole concentration with what? With the position of the Fermi energy level in band diagram. So now in this example, we have combined all the concepts that we have learned from the first week to the fourth week now. Okay, so if you can find out the Fermi energy level in the band diagram, you can also find out the doping concentration as well as electron concentration stuff. And here maybe you may answer this kind of question. So your sample, silicon sample, has this band diagram. 36 electron volt. What is the whole concentration? Can you calculate it? The answer is very simple. Let me show you my logics in my brain. Aha, here EF minus EI is 0.36. That is something times 0.06. So something is 6. Okay, then this EF is close to the EC. So this should be n-type silicon material. So electron concentration or major carrier concentration is 10 to the 1, and the next digit came from here, 6, right? 6 coming here. But the question is P, whole concentration, minority carrier concentration. Okay, let's use a mass action law. N times P is equal to Ni squared. This is silicon, so 10 billion squared. And now I know this number 10 to the 16 from the energy band diagram. Okay, and P. Therefore, P is 10 to the 4 per cubic centimeter. This is the answer. So you don't need to write down these whole steps. Simply, you can write down the answer. I definitely strongly believe your mathematical skill. Okay? And now let's do reverse process. You have a N-type. You have an N-type silicon sample, and doping concentration is 10 to the 17 per cubic centimeter. Can you draw the energy band diagram of this N-type silicon material? Definitely you can do that. Because there is 7 times 0.06. So the answer is just to draw the two parallel lines. And here is intrinsic Fermi energy level. And I said 7 times 6. Yeah. Here, 0.42 electron volt. That's the answer. Okay. So very simple. So practice with your own example. Okay. All right. And I have just explained this left-hand side, and let's do the right-hand side. It's very simple. Instead of n, I have used the p, and ni is kind of constant, so I have used the same constant. And here ef minus ei, here ei minus ef. Why is that? Because this, I would like to tell you the p-type silicon material. In p-type silicon material, there are many holes, right? and very few electrons available. So herein, intuitively, you can guess the position of Fermi energy level. What is the meaning of the Fermi energy level? We said energy level at which the probability of finding electron is 1/2. Okay, that kind of electron energy has been written as Fermi energy level. Take a look at here. Well, if it was intrinsic silicon material, valence band is almost filled with electrons and conduction band is almost empty. No electron, all electron. So Fermi energy level is kind of half and half, 50% energy level. So maybe in the middle of the band gap energy. So this physics is still working and valid in explaining the p-type silicon material. So now this energy band diagram showing the p-type silicon material case. So almost no electron, and here it should have been filled with many electrons, but many holes are available, which means the probability of finding electron with a 50% should not be existing in the middle. It should be shifted downward because this valence band is now fully filled with electrons. Okay, so Fermi energy level should be found near to the valence band edges. Okay, so now here Fermi energy level is below E sub I, mid gap. Okay, so how much EF is away from the mid gap EI would determine the hole concentration. So for example, the hole concentration, suppose that EC, EV, and EI, your Fermi energy level is here, and this energy difference is say 0.24 electron volt. What is the hole concentration? That's easy, 0.24, okay, 0.06 electron volt times what? 4. Okay, then this EF is close to the EV, so P-type. Majority carrier is whole, so majority carrier concentration or whole concentration is 10 to the 1, what? 4. Plug in here. So the answer is whole concentration is 10 to the 14 per cubic centimeter. It's quite simple, right? But you do use this equation. Just plug in here. EI minus EF is 0.24 electron volt. Plug in. And then Ni is 10 to the 10. And solve this equation to get the P. You're going to end up with a 10 to the 14 in the end. Okay. So let's one more practice here. Whole concentration is say 10 to the 19. Where is EF? Very simple. Now the whole concentration is 10 to the 90, which is much higher than n sub I, 10 to the 10. So this is p-type silicon material. So in p-type silicon material, the Fermi energy level should be found near the band gap, near the valence band edge, EV. So maybe about here. And what is the energy difference? EI minus EF. That is, just take a 9. 9 times 0.06 electron volt, 0.54 electron volt. This half band gap is, 0.56 electron volt, and here the EI minus EF is 0.54. So EF is almost equal to the EV. So this drawing is quite wrong. Let me redraw it again. This is almost equal to the EF. So this is the right answer. So EF is almost equal to the E sub V. Okay, so now I'm going to tell you some definition of non-degeneratively doped semiconductor or degeneratedly doped semiconductor. So degeneratedly, the meaning of this word is quite complicated. So instead of using degeneratedly, you can use a heavily doped. Okay? So once you're using a non-degeneratedly one, means a lightly doped semiconductor. So depending on the doping concentration, we can precisely estimate the position of the Fermi energy level in the band diagram. Okay? That we have just done, right? From this sample question, we can estimate the Fermi energy level position once we know the doping concentration, or vice versa. Once you know where the Fermi energy level, you can estimate the doping concentration as well. So herein, depending on the doping concentration, we can classify the semiconductor with the two different types, heavily doped or lightly doped. So what is the main criteria to classify it? Here is the answer. Heavily doped one means 10 to the 19 or beyond, 18 or beyond. I guess there we go. Here is the criteria. If donor's concentration is higher than 1.6 times 10 to the 18, then we can say that this n-type silicon material is degeneratedly doped. Otherwise, say Nd is 10 to the 16, then this silicon is lightly doped. What about the acceptor's concentration? That is 9.1. That's too complicated. Just ignore the number and 10 to the 18. Okay. So the doping concentration is higher than 10 to the 18. Then this semiconductor material is heavily doped. Otherwise, it is lightly doped. In energy band diagram, if your Fermi energy level, the position of Fermi energy level is near to the conduction band edge in n-type case, the EF minus 10 to the 18 means 8 times 0.06 is 0.48 electron volt. But this half band gap is 0.56 electron volt. See, only 0.08 electron volt, 8 milli electron volt. See, the total band gap is 1,120 milli electron volt. So 8 out of 1120, you can ignore it. So if doping concentration is 10 to the 18 or higher, your E sub F Fermi energy level is almost stuck to the conduction band edge. Okay. So 10 to the 18 is degeneratedly doped semiconductor. Okay, which means EF is almost equal to EC. The position of Fermi energy level close to the band edge indicates heavily doped semiconductor one. Okay, so from now on, I'm going to use N plus doped instead of N doped. Okay, which means N plus means it is very heavily doped. So more quantitatively, if I'm saying this is heavily doped, you always come up with the number 10 to the 18. Okay. So 10 to the 18 is a criteria to determine if this semiconductor is heavily doped or lightly doped. Okay, and in this slide, the message is, can we use a Boltzmann approximation for all the doping concentration ranges? Well, actually, no, it is not allowed to use a Boltzmann approximation over all the doping concentration. However, we can accept to use a Boltzmann approximation with a certain amount of error rate. Okay, so with a certain error rate, less than 5% error, we can still adopt the Boltzmann approximation. So 5% error rate, where does it come from? It comes from this number 3 kT. So 3 kT, if this Fermi energy level can be found within this regime or that region, then Boltzmann approximation cannot be used. However, we can use it with a certain amount of error. So the error rate is 5%. So 5% error could be acceptable. Okay? But in this lecture note and textbook said Boltzmann approximation is only valid when the Fermi energy level is placed in this range. Okay, so Fermi energy level is placed in this range, then we can use Boltzmann approximation. But we can use it for all the doping concentration range. Okay, I guess you can solve this example problem. The example is quite simple, so you can do that by yourself. And I have explained the heavy doping and lightly doped one. Okay, bandgap narrowing, so I will explain it in next week. And mobile charge carrier from this chapter 3, mobile charge carrier will be explained. So that's all for today's lecture, and I guess I need to decide if we keep using real-time streaming lecture or not. So I'm going to discuss with a teaching assistant, and we'll ask another professors how to run the classes. So I guess a few student has some idea. Please record your lectures, and then we can take a listen whenever we are convenient. So that's a good idea, I guess. So maybe please take a look at the official announcement in iCampus. I will post my official announcement sooner or later. Okay. All right. So if you have any question, leave a text message on the chatting window or email TA or post your question in iCampus. I will do my best to get back to you. And regarding how to run this class, I'm going to officially decide to use WebEx or not sooner or later. So I'll post it soon. Okay, that's all for today's lecture, and thank you for attending my lecture, and see you next week. That's all. Bye bye.
원래 1분이요? 아니 15분이니까 2 45분이구나. 이제 15분 뒤에 하지.
네, who is talking? 누가 박유찬 학생 얘기하는 거 들리는데요. 질문이 있나요? Any question? 마이크를 껐습니다. 다 보입니다. 호스트라서 다 보입니다. 여러분이 누가 마이크를 켰는지 껐는지 다 보입니다. 질문 있으면 뭐 한국말로 물어봐도 됩니다. 물어보세요. 내가 영어로 다 바꿔줄 테니까. Any question? No? No question? 오케이. 그러면 이걸로 마치겠습니다. 수고했습니다. That's it. See you next week.